Welcome to the Henai Star Docent Training Series. We're going to start off talking about vectors. Vectors are a way we measure many different things in physics, ranging from distance to forces to things like momentum. So vectors are used quite extensively in physics. You're used to the idea of a scalar. A scalar is just a number. 60 miles an hour is a scalar, for example. So 60 miles an hour is a scalar. What makes that a vector is when we add direction. Okay, so we add direction. So my scalar may very well be my speed. Okay, speed is equal to 60 miles per hour. Okay, but my velocity vector, and for vectors we typically put a bar over it, that might be 60 miles per hour in the northeast. Okay, 60 miles per hour in the northeast. So speed is 60 miles an hour, but the velocity vector is 60 miles per hour plus the direction northeast. Now, typically we don't worry too awfully much about specifying northeast, northwest, southeast, southwest for directions. So how do we normally specify a vector? Say we've got vector A. Okay, we've got vector A. We could specify it as a magnitude. Okay, a magnitude of say 6. And we could specify an angle. Maybe if we come over here we have our Cartesian coordinate and I've got a vector like that. Alright, and then I might have an angle off of the angle theta here. Okay, so I could specify that might be an angle of say 35 degrees. Alright, so I've got a magnitude of 6 and a angle of 35 degrees. That's kind of a cumbersome way of doing things, however. That's a very cumbersome way. So what we normally do is in 2-space, in our Cartesian coordinate systems, in 2-space, what we'll do is we'll give the x and y coordinate of the vector. Okay, so we have our 2-space here, and I've got a vector. Alright, and so the difference here in x and the difference here in y, so delta y, delta x, okay, those are the values of my vector, and they imply a direction. So my vector A here will have delta x and delta y. Okay, so delta x and delta y. Or because we can take this vector and we can move it anywhere in my Cartesian space, it's going to still have the same x component, it's going to have the same y component, and it's going to have the same length and same angle relative to the x-axis or the y-axis. So what we're going to do, now this also plays into trigonometry very nicely, because there is, of course, a vector here, or an angle here of theta. Okay, angle of theta, that's a very poor theta. And so one way of looking at, so that's the length of my vector, length L. So L is going to be equal to the square root of delta x squared plus delta y squared, Pythagorean theorem. Okay, so just take the square root of those two, so that's my magnitude. Now, the way trigonometry works, my delta x, okay, is going to be equal to L times the cosine of theta, and delta y will be equal to L times the sine of theta. Okay, so we'll rearrange terms here, and delta x over L is equal to cosine of theta and delta y over L is equal to sine of theta. Okay. Well, the other thing, if I know what my x and y is, I can compute my L. If I know what my x and y is, I can turn around and compute my theta. Okay. So theta in this case, theta is going to be equal to the inverse cosine of delta x over the length. Okay, basic trigonometry. Okay, so from those, my delta x, delta y, or my x and y components, I can turn around and compute everything else that I need to know about this vector. Okay, so what are some other things about vectors that we need to know? Okay, so let's say we have two position vectors. So we'll call these two position vectors P1 and P2. Now, a lot of times we use P to denote angular or momentum, but in this case we're going to use the P notation for position vectors. So my first position vector, we'll give it a value of x of 3 and y of 4. Okay, and then the second position vector, we'll give it -1 and 2. Okay, so what can we do with these two vectors? What can we do with these two vectors? Well, first off, we can do a thing called scalar multiplication, where we're going to take the first vector and we're going to multiply that by 2. So I'm going to say 2 times P1. Well, that's going to simply multiply x by 2 and y by 2. Okay, so doing scalar multiplication of a vector simply takes each one of the components and multiplies it by the scalar value. But say I want to do something with these two vectors. Let's say I want to do vector 1 plus vector 2. Where's that going to take me? Okay, so I've got these two vectors. One goes, well, let's come down here. We'll take a look at this. So Cartesian coordinate, we'll assume that we start at 0. We go over 3 and up 4. Okay, and that we end up there. So there's my up over 3 and up 4. But what I want to do is I then want to add 2. Well, that's going to go back 1 and up 2 to there. And the resulting vector is going to be from the head of the first vector all the way to the tail of the second vector. Okay, so that's my answer vector right there. Well, how do I get there? P1 equals P2 plus P2. Well, I'm going to take 3 plus -1, comma, 4 plus 2, or my final vector is going to be 2 and 6. Well, that makes sense. In both cases, I went in the first case in x, I went over 3 and back 1. That gives me 2. And for the y coordinates, I went up 4, and then I went up 2 more, so that gives me 6. So vector addition is simply adding the two sets of components together. I add my x components together, I add my y components together. Vector subtraction is the same thing. We subtract our components one element at a time. So those are a couple of the big mathematical things that we do with vectors. There is one other thing we're going to talk about. There is no vector multiplication per se, but we're going to talk about a dot product. Okay, so I'm going to have P1, and I'm going to dot that into P2. Okay, well, what does that mean? What that's basically going to do, that's going to give me a scalar value. It's not going to be a vector. It's going to be a scalar. And what is that scalar value going to be? What is that going to be? Okay. Okay, so the next thing we want to talk about here is simply a notation, a description. So one of the things I've got is I've got a vector A, okay, and I want to know what the length of that vector is. What is its length? Okay, what's its length? Well, obviously, we use the Pythagorean theorem. We take the x component, square it, sum that with the y component squared, take the square root of that, gives us the length. But what notation do we use for that? So the notation that we use for length is going to be the absolute value of the vector. So when we talk about or mention the absolute value of a vector, that refers to its length.